Hi everyone, my name is Pustogarov and I'll be presenting a paper Ex-vivo dynamic analysis framework for Android device drivers, which is a joint work with Qian and David Lee. So what makes Android drivers a source of a large number of bugs? Porting Android to a new board requires developing new drivers for this board. At the same time, Android smartphones is a highly competitive market, which makes manufacturers release new models in a rush and focus on functionality and features at the price of security. As a result, up to 80% of kernel bugs are bugs found in device drivers, which are a source of privilege escalation attacks. Let me briefly recap a few things about Android. Android kernels are based on the Linux kernel, and in Linux, drivers, once loaded, become a part of the kernel with the same privileges, which means the compromised driver code compromises the whole kernel. In order for the user space to be able to control the peripheral, drivers create a special device file, using which a user space application can issue IOCTL'S system calls to send commands to the driver, which are then passed to the hardware device. What is unique about IOCTL'S system calls is that in order to support a large number of use cases and the hardware features, IOCTL'S system calls accept arbitrary complex structures as input, which is then parsed by the driver, and this complex parsing is often bug-prone. Dynamic analysis can be very useful in finding and understanding kernel bugs. Examples of useful dynamic analysis techniques are coverage-based fuzzing or interactive debugging. Dynamic analysis of Android drivers is currently possible on-device. On-device analysis has some important limitations, though. First, it makes the analysis expensive, as one needs to buy as many smartphones as he wants to analyze. Second, often one needs to reflash the device which is not possible for devices with a locked bootloader. This makes on-device dynamic analysis difficult. And in this work, we ask how can we move the analysis off-device to an emulator. The answer is it is challenging. There are two reasons for that. First, drivers obviously expect to be able to speak to the peripheral while executing. These peripherals are not provided by the current emulators, and adding them is a significant effort by itself. Second, drivers depend on the host kernel on which they were meant to run. But at the same time, very few hardware-specific kernels can boot inside emulators for the very same reason. They expect some specific hardware to be present. This means that the straightforward approach would be to emulate new peripheral and port the driver to a kernel that can boot in QEMU, which is a lot of effort for every new driver and doesn't really sound too promising. But let's take a step back and see in more detail how these dependencies look like in the actual code. This slide shows a simplified version of a camera driver for MSM Android kernel. The user space can issue IOCTL commands and retrieve some data from the camera. The upper part of the slide shows the part of the code immediately after the execution entered the kernel space. Later, the execution goes to the code in which the driver first retrieves an array of bytes from the hardware as data PTR and then copies it to user space. What is interesting about this specific example is that while the data from the hardware is passed between different parts of the driver, it is not used to make any control flow decisions. In other words, the value returned from the peripheral doesn't matter for successful driver execution. This gets us to the idea of superficially dependent paths. When the driver executes, there are two types of paths. Paths that really need to receive specific values from the hardware or the original kernel. And there are paths, which we call superficially dependent paths, that only need the peripheral or the original kernel more as a formality. They might need to be able to speak to them, but the actual return value or function call side effects don't matter. After analyzing different drivers, we ended up with two hypotheses. First, there are many superficially dependent paths and they contain vulnerabilities. Second, initialization code for many drivers consists of superficially dependent paths. We need this second hypothesis because drivers do a lot of stuff before we can call IOCTL. For example, they need to create a def file. If these hypotheses are correct, we don't need to model the hardware precisely to find bugs, and thus we can construct an evasion system that satisfies hardware and software dependencies by evading them. and it will be sufficient enough to load drivers and find vulnerabilities. We won't be able to find all bugs, but we'll be able to find some bugs. We verify these hypotheses by actually building the evasion framework in which we can load unmodified Android drivers. The heart of the evasion technique is the evasion kernel, which is based on vanilla Linux kernel, and its purpose is to be able to load a diverse set of unmodified drivers. What it does is masking hardware and software dependencies. In a nutshell, we want to take a driver from Android kernel that cannot boot inside QEMU and plug it unmodified into our evasion kernel that can boot in QEMU, and thus can be used for off-device dynamic analysis. Because the driver was compiled for a different kernel, it has some dependencies on the Android kernel, such as some functions and a specific memory layout. And this is in addition to missing hardware, so we need to solve these problems before we can plant the driver into the alien evasion environment. I'll describe each of these dependencies in more details now, starting with missing peripherals. On a very high level, when the driver tries to speak to the peripheral, the evasion kernel simply redirects all such communication attempts to a zeroed-out memory buffer. In order to understand our approach in more detail, I need to recap how Linux kernel manages peripherals first. Android smartphones today have most peripherals integrated into a single board that do not allow automatic discovery. For such cases, the information about the peripherals can be passed to the kernel by the bootloader with the device tree file. To be more specific, below is a U-boot example where one provides the file name of the device tree file in the very same way as kernel image and the RAM disk file names. In a device tree file, each peripheral is described as a set of properties. One of them is the device ID. At step 0 in the slide, the kernel uses this ID to find the correct driver and start executing it. When the driver executes, it can read device tree properties, for example, to find out where to find the peripheral. In the example, at step 1, it queries the device tree about the physical memory location where the peripheral can be found. It then creates a virtual memory mapping for this address at step 2. And finally, the driver can speak to the peripheral using this mapping at step 3. Now, in the case of the evasion kernel, we have the driver, but we don't have the peripheral. So what the evasion kernel does is the opposite to normal operation. It looks at the ID of the driver and finds or creates a device tree entry with this ID. This fake entry is not backed by actual peripheral and allows the driver code to execute unmodified and read the corresponding properties. Next is step 2, where during normal operation the driver would map the real device's physical memory location. We redirect this mapping to zeroed page. In this way, at step 3, the driver has an illusion that it can read and write to the missing peripheral without a crash. Let's now move to missing software dependencies. The reason for software dependencies is that drivers come from various Android kernels that add new functions that evasion kernel doesn't implement. There are two types of software dependencies: missing symbols and unknown driver memory layout. In a nutshell, we simply replace these missing functions with function stubs. At the early stages of driver loading, the kernel does relocation. It maps function names that the driver uses to function implementations inside the kernel. In the case of a known symbol, such as print_k, the evasion kernel just does the relocation as usual. In the case of missing symbols that are not implemented by the vanilla kernel and hence by the evasion kernel, our system maps them to a set of function stubs. We define 3 different stubs. We map missing functions whose return type is a pointer to a stub that allocates a chunk of memory. Otherwise, we map it to a stub that always returns 0. This is based on the Linux kernel convention to return 0 code on success. The second problem when trying to load a driver compiled for a different kernel is difference in memory layouts. Let me explain it using the struct file below. The definition of this structure has a field guarded by a configuration option. If the EVASION kernel at the lower part of the slide was compiled with the configuration option set, and the driver was compiled with that option unset, they will end up with different structure layouts. They will have different fields at the same offset x. What it means is that when the kernel tries to speak to the driver and pass struct file as an argument to one of the driver's function, they will assume different offsets, which will result in that the driver will think that it writes one field, while in fact writing to another, and thus corrupting the structure. In order to guarantee the same structure layouts in memory, the EVASION framework analyzes the EVASION kernel and the driver binaries and identifies when their memory layouts are different, and suggests how to correct it. So now we have these three hardware and software dependencies evasion techniques, and we can use them to verify our hypothesis about superficially dependent paths. In order to check that there are many superficially dependent paths and they contain vulnerabilities, we checked a list of 26 known bugs from 10 different drivers and checked if we can trigger them with our system. We were able to do that in 80% of cases, which confirms our first hypothesis. In order to check our second hypothesis, we tried to load 62 other drivers and check if we can successfully initialize them up to the point where they create a file in that folder. We were able to do that in 77% of cases, and this verifies our second hypothesis. While at this point the evasion is useful to analyze existing bugs, the other important question is whether we can find new bugs. In order to figure it out, we developed a new framework for fuzzing IOCTL'S. In our fuzzing framework, we wanted to make use of user space tools as there are a large variety of them, and they are much easier to use and set up than dedicated kernel space tools. In a nutshell, when the evasion kernel initialized the driver, we take its complete snapshot and run it inside a CPU-only emulator as a regular user space program, which we can then fuzz with any user space fuzzer. I will not go into all specific details of this approach, except for some details of how we deal with intricacies of IOCTL fuzzing. So one of the complications with IOCTL system call fuzzing is that it accepts arbitrary complex structures as input, which makes it a hard target for fuzzing. Let me explain with an example. Assume that an IOCTL system call accepts a structure on the left of the slide. It has two fields that should be valid pointers and point to arrays whose sizes are determined by two other fields. Such complex field interdependencies are hard to figure out with purely static analysis. In case we use a naive approach to choose fuzzing seeds, something like as shown below, and provide a flat random byte array as input during fuzzing, the driver won't find pointers at expected locations, and we won't be able to trigger many new paths. In our framework, we use the fact that user space pointers and the sizes of the arrays they point to usually go through copy from user interface. This is done due to security reasons, and not doing it is a bug by itself. So we instrument copy from user functions to intercept these pointers and sizes. If we go back to our example, the location of the field that should contain a pointer will appear in the copy from user function as the second argument. And the size of the array it points to will appear at the third argument. In a simplified way, this is how we learn what parts of the structure should contain pointers, and we also learn field interdependencies. Now, putting everything together, we tested our evasion fuzzing framework to fuzz IOCTL'S in 32 drivers from 2 different kernels and discovered 29 bugs in total. 12 of which were confirmed to be new bugs. We also had only 5 false positives. This confirms that evasion is efficient enough to find new bugs with a low false positive rate. Let me now go through some of the limitations of our framework. First, it is currently most suitable for system call analysis when the malicious input comes from user space applications. And, for example, it would be hard to use it for Wi-Fi drivers. Second, evasion can produce false positives, which is usually not the case for fuzzing. However, in our experiments, the false positive rate was quite low. In summary, we observed that there are many superficially dependent paths, and they contain vulnerabilities in driver code. We also developed a set of techniques and a kernel that allowed us to load and initialize Android drivers inside an alien environment and carry out off-device dynamic analysis of these superficially dependent paths without the need to port drivers or having to emulate new hardware. We also introduced a way to transplant and fuzz drivers in user space. And finally, we found new bugs. This concludes my presentation. Thank you very much.